Having gone through developing points on the unit circle for rotations of pi over 4 and evaluating trig functions for those rotations, I think it's a good idea to take a look at a circle that does not have radius 1. In particular, for 45 degrees, when we think of a right triangle for 45 degrees, we think of the 45, 45, 90 triangle, and we tend to think of sides of length 1 and a hypotenuse of radical 2, right? So I could use a circle of radius radical 2, and when I do that, the triangle associated with the rotation of pi over 4 is exactly the triangle that I've drawn here. So the length here, which is my x-coordinate, is exactly 1. And the length here, which is my y-coordinate, is also exactly 1. So the benefit to using a radius of radical 2 is that my triangle here matches exactly what I have here. I don't have to scale down to a hypotenuse of length 1. The trade-off, when I evaluate cosine of pi over 4, I have to remember that I'm going to take my x-coordinate and divide by my radius. We actually divide by our radius when we use the unit circle. It just so happens to be 1, so the effect is minimal. Okay. So, pi over 4 on a circle of radius radical 2 gets the point 1, 1. We can use our symmetries to figure out the other points. So let's use these points to evaluate, let's do tangent of 3 pi over 4. Pi over 4 lands me in quadrant 2. I'm going to have the point -1, 1 when my radius is the square root of 2. So, a couple ways to think about this. Maybe you remember that tangent on a circle is defined to be y over x. So my y-coordinate is 1, my x-coordinate is -1. So tangent of 3 pi over 4 is -1. Maybe instead, and I think it's a little more natural, maybe instead we think in terms of sine over the cosine. Right? Well, the sine of 3 pi over 4, using a circle of radius radical 2, is the y-coordinate divided by the radius. And the cosine is going to be the x-coordinate divided by the radius. Right? So either method, or either way of thinking through the problem, we'll get a tangent of 3 pi over 4 equal to -1.